CP campers, this is our first installment on our unit of moles and reactions. So now we're really getting into the chemistry. Okay, so we learned a little bit about bonding before. We've talked about naming compounds, writing formulas. You're going to see why writing formulas are extremely important. It comes in with calculations, simple calculations, though. Don't get nervous about it. It is just algebra, you know, adding things up and then dividing by a total number. So don't freak out when I say, oh, there's some calculations that are going to be involved. We will always be talking about dimensional analysis throughout chem, but just remember that's just fancy words for crossing out units or converting from one thing to another. So when we talk about moles, and this is like an odd thing, you know, historically I should look into why they ended up calling the unit a mole. I'm assuming it's because if you look at the word molecule, it's long to write out. There really isn't a abbreviation for molecule. So if you want a measurement unit that represents how many molecules are there, they came up with a unit, a mole. And if you have more than one, you have moles for plural. So that, I think, is where this started out. It really came from that word molecule, and you're going to measure the number of molecules that are there, so we call it a mole. All right, so let me move this up just a little bit. So when we look at what is a mole, it is a unit of measure, and that's what it is. It is very similar to the things like we say, go get a dozen of eggs. Well, we know a dozen of eggs comes in a carton, and it's 12 in a dozen. We can say, go get a carton of soda, and it depends on which way you do it. If you get one of those smaller cartons, like you can put your little fingertips through and grab and run, there's 12 cans in that carton of soda. If we say we want a case of soda, there's 24 cans in a case of soda. So moles really is a unit of measure. That's all it really is. It's how we measure things. Well, I don't have my little gloves, so this might screw up. Again, similar when we say we have 1 dozen of eggs. It's a relationship here. We have 12 eggs. Right? We have a carton of soda. We have 12 cans. A ton. Right? If we want a case of something, we have 24 cans. So when we talk about a mole, and it depends on the context we use it in, mole will mean different things to different people. In terms, and I shouldn't say different things to different people, but the unit of a mole means how much do I have under those conditions of the material I'm looking at. Because each material will have its own measure for a mole. And that's where it gets a little confusing to people. Now, moles for chemists are very important because it's a relative measure. It's how you compare things. It's how you keep track of substances you've made, substances you need to use. So it's again, quantity. We celebrate it on Mole Day, and you'll see why. If you are interested in learning more about things and events for Mole Day, there is an organization called moleday.org. It has a website. It actually has a shop, and you can buy cute mole things in there. Normally, I give you guys Mole Day tattoos, so I'll see how we'll do this. Figure out either how to get them to you. It's not something I would have you put on in class this year because I used shared applicators, so it's not something I can do then. And we'll just figure out what we're going to do to celebrate mole in a proper way. So when you talk about moles, you have to keep in mind, am I using the mole in describing a compound? So then we're talking about how many molecules we have there. Okay, so when I say I have a mole of a compound, I have a certain number of molecules. When I'm talking about the mole of an atom, we're talking about an element. And then there comes this very nebulous term of, oh, well, I need a mole of these particles. Remember we talked about electrons and photons before when we did energy or light? So When you talk about particles, that could be a mole of protons, a mole of photons, a mole of neutrons. What are the individual particles that are there? You can have a mole of Skittles if you want. I always refer to food. A mole of pizzas. We could feed the world for a really long time with a mole of pizzas. So it is, again, unit of measure. So there's four ways. I'll say 4 ways that we say we have a mole of something. So the first way has to do with the formula. So when we look at a compound, writing the formula tells us a molar relationship. It tells us how many atoms of a particular element are present in one molecule. Okay, so that's a mouthful, right? So when we have a formula, like a chemical formula, that tells us the number of atoms of an element present in that compound. Now, here's the thing. We call that the subscript. And that subscript is what we call a molar ratio. Right? If I look at this formula of aluminum sulfate, in aluminum sulfate, I have 2 moles of aluminum to every 3 moles of sulfur and 12 moles of oxygen. You might say, wait, I don't see a 3 by the sulfur. Oh, but it's over here. That 3, that subscript gets distributed into the parentheses just like algebra. There's that dirty word again, that mathematics. Right, so I multiply the subscripts together, and that tells me how many moles of each atom I have. So those are the moles of atoms in the formula. Now, when you go further to that, how do I say this? A mole of aluminum sulfate also has associated with it a weight, how much that would weigh when you took 1 atom of, or I shouldn't say 1 atom, 2 atoms of aluminum, 3 atoms of sulfur, 12 atoms of oxygen, and it's all bonded together. And if I have 1 molecule, then it has a certain amount of weight, and that would be the weight of 1 mole of the material. It's kind of going to be like a circular thing. You're going to say, wait a minute, didn't you just say it? And it's like this circular thing that goes round and round about the relationships between them. You have to be able to count subscripts. Subscripts are important so that you know what's there. You can't ignore them. And again, if they ask you how many moles of atoms in a molecule, you go to a subscript. Okay, now you have to be careful. Because it's a ratio. It's a ratio there, and it does link to a special number, which is Avogadro's number, which you can see on the paper, and we're going to talk about in a minute. So keep this in mind, that these are ways to link the unit called a mole all together. If you look at the other formula that's here, the copper sulfate that's here, but the copper sulfate is what we call a hydrated crystal. Okay, hydrated crystal. And hydrated means that water is stuck in it. So I'm going to use the term hydrated crystal. Okay, if I told you all we had was just CuSO4, and we got it from that crystal, this would be considered the anhydrous without water. Part of the crystal. So this dot in the middle, and this is what can get confusing, because a lot of times we relate what we do in chemistry back to math, but this is the tough part. This wonderful little dot in here does not mean multiplication. It means that when the copper sulfate made its crystal lattice and it was forming, it trapped water molecules in it. So when we want to look at 1 mole of that material, it is the combination of the two things together that make up 1 mole of material, because the water's trapped inside. So this is what gets confusing, because in math we would say a dot means multiplication. In a chemical formula, the dot means add the weight of the two things together to get the weight of 1 mole of the material. So that's why I call it an adding dot. It's not a multiplying dot. You add the weight of the two things together. And it's not just 1 water. In this case, there's 5 waters. Again, 1 mole of that particular material. That coefficient in front of the water will change depending on the hydrated crystal. I think it's sodium sulfate has 12 waters. I'm trying to remember, there's a few others. One has 3. So it depends on what material you have there. Okay, so now, here comes the calculation part. And I'm going to move this up so we can focus on the calculation part. It's not rocket science, thank goodness. It can lead to rocket science, but it's not rocket science. Alrighty, so in order to calculate and put a numeric value, besides counting atoms, to the meaning of a mole, we can do this thing called gram atomic mass, or formula mass, or molecular formula mass, or gram formula mass, formula weight. Some people call it weight. I'm trying to think. There's other acronyms to it. It's not really acronyms. They're interchangeable. If somebody says, what's the formula mass, they're asking you how much does the molecule weigh for 1 mole of that molecule or that compound. If they say, what's the gram formula mass, it's the same thing. If they say, what's the atomic mass of 1 mole of that compound, then that would be, again, how much does it weigh for 1 mole. How do you do that? You look at what makes up the material. This is where formula writing becomes really important, because if they give you a name and they say, what's the formula mass of this, you have to have the formula correct in order to calculate your formula mass, true formula mass, the correct formula mass. So when we look at aluminum sulfate, we said that there were 2 aluminums. So I list things out when I do these. So here's 2 aluminums, and I want you to do this. I know some of you are going to be like, I can do this. I don't need to make a list. I can just type it into my computer, my calculator, my TI, because my TI has a nice display. Yes, your TI has a nice display, but a grader, a reader, and myself do not get to see your TI display. Only you do. So please write it down so we can give you credit for showing your work. So as we go through again, we distribute the 3. The 3 goes to the subscript there, and then we multiply 3 times 4, so we get 12. So now I have 3 sulfurs and 12 oxygens. Now I go to the periodic table and I look up the mass. Now what I'm going to tell you here, this was notes that I copied really quickly, but in AP, they want you to use 2 decimal places. And I'll tell you, it kind of depends on what they give you too. Because if they give you a whole number, and your whole number is like 12 grams, they say, oh, you're given 12 grams of the material. Don't bother with the decimal places, because you can't have any more than 2 sig figs anyway, because you're going to do 12 grams divided by your formula weight, and that 12 will dictate the sig figs. So why go the extra part of doing the tens places? But I'm going to say to you that in AP, the readers say use 2 decimal places for the weight. I did not do that here. Okay, and I'm not going to have you practice this tonight. I just want you to take notes on it. Then I'm going to revisit it tomorrow, depending on how far we get about going over the other homework with practicing your diagrams and everything. So again, this comes off the periodic table, and now you multiply it out. If I have 2 aluminums, then the total mass given to me by the aluminum is 2 times its weight. So my total mass given to me by the aluminum in that formula is 54. For sulfur, we said there were 3 sulfurs, so the total mass attributed to sulfur in the formula has to be 3 times the 32. I think it's 32.06 off the periodic table. So if you're going to do the 2 decimal places, it would be the 32.06, which would end up being 96.18. Would it change this? Maybe. Aluminum's 27. No, it's 26.998. It's really high to 27. So you could do that, and that would bring it down 3. So probably no. We're probably not going to wind up higher. This is definitely 16 because oxygen's 15.999 something. So we always use 16 for oxygen. So I find the masses of each of those, and then I add them up, and I get a total, and the unit I'll put is grams per mole. You could also call that atomic mass units, but we usually make sure that we label it. There are so many grams per 1 mole of that material. This now becomes a conversion factor. You've just created a conversion factor between what a mole is and what your grams are. And then if you can convert from grams to moles, you can go back out to volume, or you can go to number of particles. So now we have this conversion factor by having a formula mass. The 2 other definitions right now, because we're going to really go build and build and build and get like nitty-picky on this later. The 2 other definitions are Avogadro's number, which is a constant. You do not have to memorize this for AP, but it is not on your reference table in Regents. So it's really 6.022 times 10 to the 23rd, anything per mole. I can have 6.02 times 10 to the 23rd pizzas per mole. Can you imagine that? Having 23 places. So move your decimal place 2 to the right, go to 602, and then put 21 zeros after that. That's how many pizzas we'd have if we had a mole of pizza. Again, if you want a mole of Skittles, we'd have 6.02 times 10 to the 23rd Skittles. I wonder how much volume that would take up. That would take up an awful lot of volume. If you take a mole of pennies and you give somebody a mole of pennies, and they can have so much money that you can feed the world for, I can't remember how many years they calculated that out to be. It's like ridiculous. If you took a piece of paper, like the printer paper, and you stacked it on top of each other, I believe you can go from the earth to the sun and back in a mole of printer paper pieces. So that 10 to the 23rd is a very large number of items. We talk about them as atoms, as molecules, as particles per mole in chemistry, but it's just telling you that's how much a mole is. Now, Avogadro didn't come up with that number. A German scientist, and why can't I remember his name now, came up with it. So in Germany, they do not celebrate the mole and call it Avogadro's number. They attribute it to the German scientists. They get very mad about that because they say Avogadro shouldn't be attributed number. He did tons of work with this, gases, tons of work. He is the one that came up with a very special relationship in the gas that says if you know the temperature and pressure the gas is at, the volume will reflect how many moles you have of any gas. If they're at the same temperature and pressure, if you have equal volume, you have equal number of moles. So that's where he started his moles work. And so what he ended up finding out is if you are at standard temperature and pressure, that's STP, so this gives you 2 conditions. You have to remember this, guys. You get 2 conditions when somebody says, I have STP. You get standard temperature, which is 0 degrees Celsius, 273.15 Kelvin. Right? No, there's no degree on a Kelvin because it's an absolute scale. Or standard pressure, which is 1 atmosphere, 101.3 kPa. Or, if you want to stay old-fashioned, 760 millimeters mercury, because we use millimeters of mercury in our weather pressure, which is the same as a torr. Mr. Torricelli was the one who came up with the barometer. And so we used to use torr, T-O-R-R, in honor of Mr. Torricelli, but then they turned it over to just the metric form of millimeters mercury, which then became kilopascals. And so you have to realize you can convert between all those units there. They're all equal standard pressure. So 1 atmosphere will equal 101.3 kilopascals, which will equal 760 millimeters mercury. Conversions, conversions, conversions. Okay, so what this is saying is if the gas, any gas, is at this temperature or pressure, 1 mole of that gas will always occupy 22.4 liters. It does not matter what the gas is. I could have hydrogen, it will occupy that volume. I could have oxygen, it will occupy that volume. I can have nitrogen, and it will occupy that volume. Notice, though, their mass would be different, but their volume is same. The mass is equal to the formula for a mole. And if I'm a gas at STP, okay, I'm going to say it again, at STP, I will occupy 22.4 liters per mole. These things here are all related, and they are a conversion fest. You can convert from one to another, back to one, back to the other, back and forth, back and forth, back and forth, till your little conversion heart is tired. But it's a conversion fest. So just remember, since my mass is equal to the formula mass, or the formula weight, if I had 1 mole of N2, I'm going to round it, we're going to call it 28, it's like 28.02, I believe. If I have 1 mole of H2, it's going to be 2.02 if I round, or 2.0, was it 0.16? And then O2 will be 32.00. These are the masses of 1 mole, but all of those occupy 22.4 liters ASTP. I can say it over and over enough. That's what it occupies. Okay, down below, just for informational purposes for right now, but we will use it a lot later on, there is a way to calculate concentration. So the one way, this is the most common way, is called molarity, because you base it on the number of moles you have. So you find the moles that you have of the material and you divide it by the liters of your total solution. And the unit is moles per liter. Now the reason why I point this out is this is one of those substitute things. If they give you molarity and they give you the volume, you can find your number of moles, because moles will be molarity times volume. And then if you know the number of moles, you can go to grams. So a lot of times you'll have problems where you go molarity. Now notice molarity is a capital block letter M, capital M, block letter. There's something else if it's script. And moles is MOL is the abbreviation. You can't go any smaller than that. If you go to a little m, you're in meters. And then you go from moles to grams. You can go backwards. You could go grams to moles to molarity, but you need to know how many liters you have. Keep that in mind for later. The other thing we're going to talk about before I end this video is this thing called a mole. I don't like it as much as my mole triangle. Okay, but a lot of people in the Mohawk Valley can relate to, if this is center court in the mall, you can go into center court from any of the arms and go back out. You can go from anywhere. I can go in here and go back out. This is what we call our conversion hub. So if I know how many grams of a substance I have, I can take the formula weight and divide by the formula weight and calculate my number of moles. If I know how many liters of material I have, I can divide by the relationship of 22.4 liters for every mole, and I'll find out my number of moles. I can start out here, and I can go in this way and back out to another side. I go through moles. Okay, now, here's my little alliteration. If you have number of moles, you will multiply to get your answer. That's a quick conversion. Okay, so multiply. We'll change the spelling. Moles multiply. If you don't, you're dividing. You're dividing by whatever the conversion factor is by the arrow. Okay, so now this is why I don't like the mole. I prefer the mole triangle. And on the mole triangle, you put the unit grams at the top apex, the center of the triangle. So if I were to say, oh, I got a triangle here. Here are my edges to my triangle. They come like this. That's a bad edge. And they go up like this. The little apexes are, or the angles, right? They are the end unit that you want to get to. Grams, liters, molecules. Right? In the center of your triangle is the unit of a mole. If you look at it this way, anything below the middle of the triangle, so anything down this way, okay, down that way, that's a constant. The conversion factor is a constant. Right? We said my constant for going to gas is 22.4 liters. My constant to going to Avogadro's molecules, number, atoms, particles, whatever we're looking for, will be 6.02 times 10 to the 23rd. Actually, they now have this baby. That one didn't used to be on the reference table. It is now on the reference table, so you don't even have to memorize that. Okay, now the only thing you have to figure out is this one. Because it is different, you have to figure this out. It is based on the formula. But if you have grams, you will always need your chemical formula mass. Okay, if you have grams anywhere mentioned in the problem, you will always need that formula weight, that formula mass. So knee-jerk reaction should be, oh, got to calculate the formula mass if they don't give it to you. Now they usually give it to you because they don't want you to spend time doing it. They want you to spend time at a higher order thing. Finding a formula weight is a straightforward mechanical process. After you get used to doing it a few times, you don't have to think. You just do it. Okay, but notice, you have to get used to doing it. It becomes intuitive. Believe it or not, that's intuition. And you're developing your intuition. Any of the other conversions, you do it essentially with dimensional analysis. Ooh, there's two words. It's no biggie though, guys. It's just multiplying or dividing, but in dimensional analysis, you're multiplying everything and you're using unit cancellation to get what you want. Right? So we're going to be doing DA, dimensional analysis, not district attorney, dimensional analysis. You start with a unit that you're given, and you got to go to the desired unit that you want. The desired goes on the top. The conversion factor goes on the bottom. You might need a third one in case you had going through the center of the mole. You're going from one leg to another. We're building. We're going to go even more than that. Ooh. So here's simple, straightforward. I have 34 grams of carbon dioxide, and I want to find out how many moles. Well, first I find its formula weight by adding up what I have in the formula. So I start with the 32 grams, and I just put it over 1. You don't have to. You can leave it out there by itself, but you have to realize it's in the numerator. And here's my conversion. I need to go to moles. 1 mole weighs 44.01 grams. Put the grams on the bottom, so this unit cancels. Ta-da! And now I'm left with moles. Not that difficult. I'm going to now go from molecules to moles. Okay, so now this is a set conversion. This is a constant. Constant. I take, and this is where using scientific notation in your calculator, that EE button makes a big difference because now you got funky numbers to multiply and divide by. So try to get used to using that EE number like we did at the very beginning when we first started practicing scientific notation. Okay, so I take my 9.61 times 10 to the 21st molecules. And this should have molecules down here. I left that out. And this is what I mean. I hate writing the word molecules. I just know my molecules cancel. There's no real, there's no abbreviation for that. Because if you try to abbreviate it, you get to mole. Well, we can't do the abbreviation that way because it's really not a mole, it's a molecule. Here's my unit mole right here. Again, the abbreviation for the unit of mole. Wow, we get to cover out one letter. Woohoo! But it saves time. It might save you a femtosecond. You never know. All right. Multiply that out, get our unit and our answer, and make sure, does this make sense? Okay, does this make sense? Well, I have 10 to the 21 divided by 10 to the 23, right? Here's my exponent part. So if I subtract that, 21 minus 23 will give me a minus 2. So we're in the right ballpark. It's a minus 2, and you have to say, is this bigger than this? Yes, it is, so that makes sense. Otherwise, it would be a minus 3 and not a minus 2. Okay, now we're going to go through the center of the mole triangle. So I have liters, and I want to go all the way out to grams. So I have to go liters into moles, and then moles out to grams. Okay, now, if I have moles, this step better be a multiplication step. Moles multiply, moles multiply. So I take my 54 liters. This is a constant. Right now, because we're at STP. And I divide by 22.4 liters. Then I multiply by the 46.01, which is the gram formula weight. And I get my number of grams. Now, I change this because this is 2 sig figs. Okay, this constant. We probably should use it as 3 sig figs because there's more numbers there. So anyway, 2 sig figs. So I'm at 110 and not 110.9. Okay, I'm going to stop there. That's more than enough for you to listen to me again at night for a half hour.